What is going on, everyone? My name is Codamore, and welcome back to the long-awaited electronics episode number 30. I just want to give a really quick thank you to all of the supporters of this series. You guys have left some great comments for me. I just want to say I appreciate every single one of them. I know I have not responded to very many of them, and I know that it's been almost a year since we posted the last episode. Just wanted to say thank you, though. It will be harder for me to continue this series now just based on my current work and living situation, but I am determined to eventually finish this series at some point in time. Thanks for sticking with me, everyone. Let's talk about the binary full adder. So before we discuss binary full adders and why we need them, let's take a look at our half adder circuit here. So the whole point of our half adder circuit was to add two 1-bit numbers together. So we can add 0 plus 0, we can add 1 plus 0, and of course we can add 1 plus 1 together to get these outputs here. And for each of our 1-bit numbers, which we call A and B, these A and B inputs that we have here, we have 2 bits of output. And the rightmost bit here, the ones place of the binary, is our sum output, while the left one is our carry output. It's these two outputs of our half adder circuit right here. Now, if you actually analyze how this addition is happening, what we're doing is we're taking this column of digits and we are performing the addition. So we know 1 plus 1 equals 2, or 1, 0. So we bring that 0 down to this place right here, and then we had to carry over that extra 1 that we had, and that simply comes down to be our carry output. In the case over here, we added this column of numbers together. We know 1 plus 0 equals 1, or 0, 1. So we bring the 1 down, and we had to carry over a 0. We didn't carry over anything, so our carry output stays at 0. Now, why am I recapping all this? Well, it's for a very important reason. This works great when we're working with two 1-bit numbers. But what if I wanted to add, 3 plus 1 together to get an answer of 4? Well, we know that 3 in binary is 1, 1. 1 in binary is 0, 1. So we have to add these together. So the process here is to take the first column, these ones here, and we perform the addition. We know that 1 plus 1 equals 2, or 1, 0. So we bring the 0 down for that column, and we have to carry over an extra 1 to the next column. And now we have to perform the addition on these 3 inputs here. So we know 1 plus 1 plus 0 is simply 2, or 1, 0 in binary. So once again, we bring down that 0 for the answer, we carry it over another 1, and that simply comes down to get our answer of 4, or 1, 0, 0 in binary. And here's the issue. We can't just chain half adders together to just magically do this, because we do not have an adder that takes in 3 inputs here. So we have to design another adder circuit to take 3 inputs instead of just 2 inputs, A and B. It needs to take a third input, being the carry in, the carry input. This way, we can chain the carry outputs of the adder that comes before it and effectively add more than just 1-bit numbers together. Let's explore this a little further. So here we have a slightly larger truth table than the last video's half adder truth table, because now we have to add 3 digits together, 3 binary digits together at once to have a full adder. We have our A and B inputs here, but we also have a third carry input. And most often, this carry input would be hooked up to the carry output of another full adder. And we'll see how to do that and why we need to do that toward the end of this video. But for now, let's figure out how to add 3 binary digits together and what the corresponding sum and carry outputs should be for those cases. So 0 plus 0 plus 0, that is an easy one. We have a sum of 0 and a carry out of 0. Can't get any easier than that. 0 plus 1 plus 0. Well, that's just 1, and we know that 1 in binary is 0, 1. So our sum bit is going to become 1, and we don't have to carry anything. It's the same thing for the next case. 1 plus 0 is just 1, so we have a sum bit of 1, and no carry out. 1 plus 1 plus 0 is going to be, of course, 2, or 1, 0 in binary. So the sum bit becomes 0, and we had to carry over that 1 bit, so we have now a 1 in our carry out position. You'll notice this is the exact same thing as our half adder truth table. But the second that we start adding the carry in bit as 1, things begin to change. 0 plus 1 is 1, so we have a sum bit of 1, carry out of 0, nothing different. 0 plus 1 is 2, 1, 0. So we have nothing in the sum bit, but we do have a carry out we had to carry over. Same for the next column. 1 plus 0 plus 1 is 2. So we have 0 in the sum bit, but we have a 1 in our carry bit, because we had to carry over that bit. And then the special case, 1 plus 1 plus 1. Of course, this equals 3, and we know that that means we need a 1, 1 as an answer. So our sum bit is going to become a 1, and we had to carry over a bit, so we have to have our carry out as a 1 as well. So we know that this is the truth table we need in order to add 3 one-digit binary numbers together, right? A, B, and carry in, which we could just call another input C. It doesn't matter what we call it. Now, how in the world can we take a truth table like this and create a circuit out of it? That seems like a pretty big task, and it's not the easiest of tasks, but let's take it slowly piece by piece. We already know a huge part to this problem. We already know that the first 4 rows here, these 4 rows, are just a binary half adder. Our carry in is 0, so that's not going to affect anything. And the truth table is the exact same thing as a binary half adder. So let's start with that circuit. We'll have our inputs, A and B, and we'll just assume that carry in is 0 right now. We'll just focus on A and B, which gives us these outputs. And that's the exact same thing as a half adder. So let's create our half adder circuit here. Remember, that's just an XOR gate, like so. Remember that this is our sum output in a half adder. And then we take A and B, and we also run them through an AND gate, like so. And that becomes your carry out from our half adder. All right, that's just our half adder circuit, and that completes the first 4 rows of this truth table, which is brilliant. Now we just have to work on these last 4 rows right here. The only difference with these last 4 rows from these first 4 rows is the fact that the carry in, this third input we have, are all 1s for all of the cases. So if we stop and think for a second, let's make this problem simpler. Rather than trying to add 3 different inputs together and determine our sum and carry outputs and making sure they don't interfere with the ones up here, we already know the sum of these 2 inputs, A and B, when carry in is equal to 0. It's just the output of our half adder. It's these sum values and carry out values up here. So rather than thinking of this as adding 3 digits together, let's just think of it as another half adder. We'll take the sum right here of A and B for each of these, and we know that that is simply 0, 1, 1, and 0. I'm just taking the sum that we know from our normal half adder, and we can then simply treat these as another half adder. Well, what's 0 plus 1? It's 1. 1, 0. All right, that matches up. What's 1 plus 1? It's 2, 1, 0. So we have a 0 for the sum bit and a 1 for the carry out. Okay, that matches up. Same thing here, 1 plus 1 equals 2. So a 0 for the sum bit, 1 for the carry out. 0 plus 1 is equal to 1. So we have a sum bit of 1 and a carry out of 1. So that's the only difference. So they all work out except for this guy right here. 0 plus 1 should just equal a 1 in the sum bit and a 0 for the carry out. But we're in luck. We know that when A and B up here are both 1 and our carry in is 0, we get a carry output. This carry output from our half adder that we've already drawn into our circuit becomes a 1. So we can simply take that carry output and just OR it with whatever carry output value we get down here in this second half adder. I'll show you what I mean. We'll go ahead and we'll take this sum output from our first half adder from these first 4 rows. So we're taking this output here, which corresponds to these that I drew right around here, and we are just adding that to the carry in bit. If the carry in bit is 0, if it stays as 0, then we're just going to keep the answer the same, 0, 1, 1, 0. Otherwise, if it's 1, we'll have these outputs that we just specified aside from this last special case. So we'll take this sum bit, and we'll take our third input, which is our carry in input. That's going to be our third input that we have. And these are going to go into an XOR gate, and we're just going to build another half adder. There we go. And we can call that our real sum bit for the binary full adder, because this sum column is all correct throughout. Everything matches up. The only difference is this carry out bit for this final 111 case. All right, let me continue. We'll take our carry in and we'll continue building this extra half adder. That simply has to go into an AND gate with whatever this input is to this half adder is. So we'll have an AND gate like so. And here's where we can see kind of the special case. We have effectively two half adders. We have this guy here, which handles the top 4 rows. We've got this guy here that handles the bottom 4 rows, except for this incorrect case. It's going to report 1, 0 in that case if carry in was 1 and the sum bit was 0. But we know that if the sum bit is 0 and it just so happens that we're at a equals 1 and b equals 1, that our first carry out here is going to equal 1. And that can fix this little discrepancy we have. And besides, we can't have two of these outputs here anyways. So we'll simply take them, these two outputs of the AND gates, and we'll simply put it through a normal OR gate. That's just going to turn on if either one of them is a 1. And that will become our carry output. I know that was a lot, but this, congratulations, is a binary full adder. And if you're not as excited as I am, let's figure out how we can use this. And after that, I'll briefly go through and kind of explain my thought process when creating this circuit again, for those of you who might want an extra explanation at the end of this video. So I mentioned that a full adder will help us add more than just two one-digit numbers together. So I used the example of let's add 3 plus 1 together to get 4. So 1, 1 plus 0, 1 equals 1, 0, 0. So if we kind of take this simple little equation here and we try to get it into a logic gate form, we can kind of sketch out what it might look like. So this first column is never going to have a carry input. There's no carry input to the first column here. So we can get away with just using a half adder. We're simply adding two 1-bit numbers together. There's no column for anything to carry over, so we don't have to worry about it. Now, I'm going to call this column of numbers input 0, I0, and this column of numbers input 1, I1, kind of representing the bit positions of all the digits. So to add the ones place of the binary of the two 2-bit numbers that we're adding, we'll simply use a half adder, right? We don't have any carry input, so we just have a half adder. That's simply going to take input 0, A, and input 0, B. We'll call this number A and this number B. And that will produce a sum bit and a carry out bit. So we know that the second column for I1, the 2's place in the binary numbers, A and B, we're going to have a potential carry. So we know this first column can result in either a 0 carry bit or a 1 carry bit. So we effectively have 3 inputs for this column here. In this case, it will carry a 1, so we'll have 1 plus 1 plus 0. So we're going to need a full adder. So we'll have one of our full adder circuits, and that is going to take in a carry input, which is just going to be the carry output of the half adder, of essentially this first column. And it'll also have I1A and I1B, these two digits right here. And of course, this will produce a sum output, and it too will produce its own carry output, essentially our third digit. So of course I'm using these boxes to represent our half adder and full adder circuits, just to reduce the amount of things we have to draw so we don't have to draw that all over again. But this lets us add those two numbers together. right? So we know that our number a is 1, 1. So I0, this digit here is a 1, so we'll pass a 1 in here. I1 for a is a 1 also, so we'll pass a 1 in right here. The first position for number b is a 1, so I0b is going to be a 1. And I1 for b is going to be a 0, so we'll add a 0 here. So this half adder is going to do its thing with these two digits. It's going to say, hey, 1 plus 1, that equals 2, so the sum bit is going to become a 0, carry out is going to be a 1. Now this full adder can start working. It knows that its carry input is a 1, because this half adder just spit out the number 1. It's carrying something. And we also know its other two inputs. So 1 plus 1 plus 0 is 2. So the sum bit is going to be a 0, and it's going to carry a 1 as its carry out. And there we go. We effectively have our three-digit answer 1, 0, 0, which is exactly what we expect. And this is brilliant because if we have more numbers, if we have an 8-bit number, if we're adding two 8-bit numbers together, for example, all we need to do is have 8 of these full adders hooked up. So if we have a full adder here, which by the way, this half adder could just be a full adder, and we can just kind of hard code the carry in to 0 because nothing will ever be carried into it. So you could make it a full adder. That's completely valid. So we'll just take, say, our full adder. The first one will have a 0 hard coded for the carry input, and it'll have its two inputs and its sum output, and it'll have its carry out. And that can just chain over to this next full adder over here with its own sum bit, its next two input digits for the places in the numbers you're adding, and it'll have its own carry out. And we can simply keep chaining these together just like this. Another full adder, sum bit, the two inputs, and its carry out, and we can just keep adding these together until we have however many bits we want to add together. So since we have two adders here, we can add two 2-bit numbers together. If we have 3 of them here, we can add two 3-bit numbers together. So that is why we needed this full adder design, is so that we can actually add however big of a binary number we want to add. So if you're making an 8-bit computer, for example, you would have an 8-bit adder in there. So you could add two 8-bit numbers together and get an 8-bit result, or a 9-bit result if you count that extra carry out bit. That's for a whole other discussion. That's it for this episode. I'm going to go through quickly again and kind of recap what we did to actually generate this circuit up here, for anyone who would like maybe a slightly different explanation on it. We looked at our truth table and we saw that the first 4 rows are just a half adder. Carry in is 0 all the time, which means we're really just adding A and B together, these 2 bits, and that truth table comes out to be the same thing as a half adder. So that's why we drew this half adder circuit right here, and we have its sum output from its XOR gate and its carry out from its AND gate right here. Then we took a look at the bottom 4 rows, and what we realized was, instead of thinking about it as a 3-digit adding problem, we can simply take the knowledge we already have of A and B being added together, which gives us this sum output, and simply add this sum to the carry in bit. So effectively, if you take the sum of A and B, right, which I'm going to try to find some space to do this. There we go. I think I kind of erased part of my diagram here, kind of redraw it. So essentially, we're taking the sum of A and B, assuming carry in is 0, 0, 1, 1, 0, and we're adding it to the carry input. So if the carry input is 0, right, if we add 0 to all these cases, then we get the exact same thing. We simply get the sum bit like that, and the carry out stays as whatever the carry out was. Of course, if the carry in becomes 1 for these 4 cases, which are these bottom rows here, we know that the sum bit will kind of change. 0 plus 1 would give us a new sum bit of 1. 1 plus 1 would give us a new sum bit of 0 and a carry out of 1. And you'll notice that this carry out of 1 differs from this carry out for that case. Same exact case right here for this 3rd row or this 7th row here. That'll give us a 0 as a sum bit and a 1 as a carry out. So even though there's no 1 as a carry out here, we know we have one in the table. And 0, 1 again gives us a 1 in the sum bit, and a 0 in the carryout, which is wrong because 1 plus 1 plus 1 should give us a 1. But since we know that the a and b, whenever they're 1, and carry in is 0, this carryout is 1. So we kind of have the cases all overlapping for the carry out cases. And of course, this first one is just 0 still. So what we were able to do is take that sum output of the first 4 rows of this first half adder and use it as an input to another half adder circuit. And the other input to that circuit would be our third input, the carry in. So if it was all zeros, if carry in was all zeros, then carry out of this yellow half adder could never be a 1. This would always be a 0 in that case. And the sum would simply be passed through effectively. If sum was 1, this sum would be 1. If sum was 0, this sum would be 0. But if carry in was, in fact, a 1, then we would be adding a 1 to whatever this sum bit was. And of course, we know that that gives us the appropriate sum bit, so that becomes the final sum of our full adder. But then the carry outs, because we have these minor discrepancies, we simply take the carry out of adder number 1, the carry out of adder number 2, and we just pass it through an OR gate. If either of them are on, we're going to make the carry out of this full adder a 1. Otherwise, if they're both off, this carry out would stay as 0, which winds up to match this truth table exactly. It was kind of tricky for me to come up with a way to actually explain my thought process of taking this truth table and converting it into a real full adder circuit. I hope it was enough for some of you. Thank you all so much for watching, and I will see you all in the next episode.